Good morning, one and all. So today we will discuss one more problem on Brayton cycle. So we have discussed the general category of problems in Brayton cycle, but in today's video, what we will be doing is we will be solving the problems on regenerative gas turbine cycle. Okay. So this is the problem. In the regenerative gas turbine cycle, air enters the compressor at 1 bar and 15 degrees Celsius. So he has given the value of pressure at state 1 and temperature at state 1. Pressure ratio beta value he has given as X. The isentropic efficiency of the compressor and turbine he has given as 0.8 and 0.85 respectively. The maximum temperature he has given, that is at state 3, which is 800 degrees Celsius. The regenerative effectiveness is 0.78. So this is the new parameter which you came across in this particular problem. The regenerative effectiveness is 0.78 and it is noted down as such here. Okay, the regenerative effectiveness is 0.78. Assume the CP value is 1.1 kilojoules per kg Kelvin and gamma is equals to 1.32 for the combustion products. He is specifying it as the value of Cp and gamma is so and so for only the combustion products, not the air. Where does the combustion products come into picture? It comes into picture during the heat addition process and during the expansion process. The only air is being compressed from 1 to 2. Okay. So efficiency we need to find in this particular problem, which is given by W net divided by QS. So W net is work done by turbine as well as the work done by compressor. The summation of these two will give you the W net. But what is QS? It is the amount of heat supplied. So in this particular thing, in the normal Brayton cycle, what happens? The heat gets supplied from 2 dash to 3, correct? Heat gets supplied from 2 dash to 3 in combustion chamber. But in the regenerative gas turbine cycle, what happens? The heat gets supplied from 5 to 3. From 2 dash to 5, it will be because of the regeneration process, which will not take into account because it is not the fresh heat added. It is regenerated heat. Okay, it is already there in the cycle. It has been reutilized from 2 dash to 5. So it is not the heat supplied, but the actual heat supplied in the combustion process is from state 5 to state 3. That means the heat supplied would be Q 5 to 3. Okay, so as it is here, so QS would be Q 5 to 3. Now, what is the compressive work? MCP initial minus final, T1 minus T2 dash, we shall say in the TS diagram. So, what is compressive work? It is MCP initial minus final, temperature difference of initial minus final. Initial is state 1 and final is state 2 dash because of compressive efficiency being given. Now, what is the heat added? Heat added is MCP. Heat added, isn't it? It is so final minus initial. Final is T3 minus T5. Okay. Now, what is the turbine work output? Turbine work output is nothing but MCP initial minus final again. So initial is 3, but final is not 4. It is 4 dash because of the turbine efficiency being given. So all those things are noted down here. So WC, WT and Q5 to 3. Now we shall calculate WC. How will you calculate WC? MCP T1 minus T2 dash is it. So you know if M is not given, the obtained answer would be per kg. So it does not make any huge difference here. Whereas the value of CP for air is 1.005 is it. So remember only air gets compressed from 1 to 2 dash. Okay, from 2 dash to 3 the combustion products or the gases will come into picture even for the process 3 to 4. So in the process 1 to 2 dash only air gets compressed. Okay. So you know the value of CP, you know the value of T1 is being given in the data and you don't know the value of T2 dash. This you have to find out. How will you find out T2 dash? First you'll find out T2 for that. Then you apply the compressive efficiency to find out T2 dash from T2. So first we shall find T2. So how will you find T2? From process 1 to 2 is adiabatic compression. So it is P1 by P2 is equals to V2 by V1 whole to the power of gamma. That is equals to T1 by T2 whole to the power of gamma divided by gamma minus 1. So P2 by P1 is beta. P1 by P2 is 1 by beta. this whole thing as it is. Substitute the things. Only T2 is unknown here. So T2 can be calculated as 480.53. Apply the compressive efficiency definition, which states that the efficiency of the compressor is given by isentropic work done by compressor divided by actual work. Isentropic work is ideal work, so no dashes involved. So it is T1 minus T2, as simple as that. Actual work is the actual work where the dash is involved, so T1 minus T2 dash. So substitute the things, only T2 dash would be unknown there, T2 dash can be calculated as 528.66. So substitute all the things in the work done expression of the compressor. So I'll get the work done by the compressor as minus 241.86 kilojoules. Since you have not substituted any mass here, it would be per kg. Okay. Now, similarly, you calculate the work done by the turbine. Now, in the turbine, you'll be having the gases, is it? So Cp of the gases, T3 minus T4 dash. You know the value of Cp, you know the value Cp of the gases is given in the problem. So T3 is given in the problem. T4 dash you don't know. So first you need to find out T4. Later you can find T4 dash from that. So how will you find T4? Apply the PVT conversion equation for the process 3 to 4. So it is P3 by P4 is equals to V4 by V3 whole to the power of gamma, that is equal to T3 by T4 whole to the power of gamma divided by gamma minus 1. Be careful, the value of gamma for the gases is 1.32, which is given in the problem. P3 by P4 is beta. Substitute the things, only T4 is unknown, so T4 can be calculated easily. And the turbine efficiency, use the turbine efficiency definition to calculate the value of T4 dash. So efficiency of the turbine is given by actual work where dash is involved, isentropic, which is ideal, just T3 minus T4. Substitute the things, only T4 dash is unknown, so T4 dash can be calculated as 751.66. So substitute the things in work done expression of the turbine, you'll get turbine work output as 353.47 positive kilojoules per kg. Because M is not substituted, it would be per kg. After that, now we will find out what is the heat supplied. So I told you in the regenerative gas turbine cycle, the heat supplied is from state 5 to state 3. So it is final minus initial, so T3 minus T5. You know the value of Cp of gas, you know the value of T3, but you don't know T5. How will you find out T5? If you refer my previous notes, you'll get this expression for a effectiveness of a regenerator. Effectiveness of a regenerator is given by actual heat transfer divided by maximum possible heat transfer. So effectiveness of the regenerator is given by this particular expression, T5 minus T2 dash divided by T4 dash minus T2 dash. If you refer the regenerative video, you'll get this once again. If you have any doubt, please refer that video once again. So effectiveness of the regenerator is being given T2 dash you know and T4 dash you know. Substitute the things, only T5 is unknown in this expression. So T5 is calculated as 702.6 Kelvin. So substitute the things in the heat supplied equation, that is Q5 to 3. When you substitute the heat supplied, you can calculate as positive of 407.44 kilojoules per kg. Now you know everything, so you know the work done by the turbine, work done by the work done into the compressor, and heat supplied. So substitute the things, your efficiency of the Brayton cycle would be 27.4 percentage. Okay. So after this, you try this particular similar problem, which is exactly similar to the previous one. But here he has asked two different things. Number one is you have to find the efficiency taking a regenerator into an account. So he has given the effectiveness of the regenerator as 85%. So take that effectiveness, find the value of T5. Your only the value of Qs would change. Qs is equals to Q5 to 3 when you take regenerator into account. When you do not take the regenerator into account, your value of Qs would be Q state 2 dash to 3. Keep this in mind. Without regenerator, Q 2 dash to 3. With the regenerator, it is Q 5 to 3. So only this difference, Qs value would change. So naturally the efficiency value would change. You need to find both the efficiency with regenerator and without regenerator. And quantity of air, if plant develops the 1065 kilowatt of power, this you know how to do from the previous problems. I think second problem, if you have solved this, the same thing is there. So kindly refer there once again and solve this. Kindly give me the mass flow rate of air for this particular problem.